Crystal growing, the art of artificially favoring crystallization, setting the right conditions for the orderly arrangement of compounds in a crystalline lattice, creating beautiful specimens of singular beauty. There are many good materials around showing simple ways to grow your crystal at home, but every once in a while we got a why. Why didn't my crystal grow? Why is it not clear? Why did it disappear after raining? Or even, how can I control crystal growth? So, how does this work to begin with? To answer these questions and to contribute to the crystal growing community, I decided to share some of the knowledge I've put together over some years in this hobby and present some practical advices on how this works and how to control the conditions to grow nice crystals at home and don't lose them. So, this is the home-based science of crystal growing. This video got longer than I expected, so I made this summary so you can know ahead what I'll talk about, and I'll cover the basics of crystal growing, temperature and its influences on crystal shape, vapor pressure, relative humidity, some phenomenon that make your crystal vanish and you might not know why, crystal quality, the evaporation rate of sodium chloride with some data of my own, also how vessel geometry and other complexity variables influences your crystal. I'll also suggest for you an easy project to perform at home and talk about my crystal chamber that I developed to stabilize the thermodynamic conditions to crystal growth. Also, in the end, I'll talk about some recommended reference. So if you are new in this video, I recommend you to go all the way through, but if you're not, just jump to the part where you left and let's begin. A quick disclaimer: crystals are of high interest to some advanced applications, so there are a bunch of journal studies, journal articles that treat this topic in depth. And my proposal here is to simplify things and present a home-based view. In other words, I'll try to abord some simple parameters like temperature, relative humidity that can be controlled at home. I will retain this video to water-soluble crystals and those that grow by evaporation method. There are a bunch of methods around, and I'll talk about this. Also, be aware, some crystals are very friendly, like table salt. You know, it's safe to eat, so it's not a big deal. But some other chemicals, like copper sulfate, might be mildly to highly toxic. So be aware of what kind of compound you're messing with. Know what you're doing before you do it. Be responsible and always think safety first. So this video is for educational purpose only. Do not use kitchen or food items for the experiments. Do not mix them as well. Always wear proper protective gear and always handle the materials with care. That said, let's move ahead. Right, let's begin with the basics. Crystal growing, and the crystal as orderly arrangement of atoms grows by adding more atoms. So here I have a sodium chloride scheme, and you see that repeating these columns of sodium chloride, I make the crystal lattice grow. This unfortunately doesn't happen if we just put a bunch of salt together, and we have to dissolve these tiny crystals in water. That's because the water molecules will involve each ion and dissolve the crystal. They will just take the ions apart from the crystal. And later on, if we take this water out, these ions will attract each other again and start reassembling the crystal. Depending on the conditions, your concentration will go up in the solution, meaning you have less water, and then you might end up with a clear crystal like this one, or with a crust like that one. How the crystal will grow, or if a crystal will grow, depends on a couple of variables. The first one is temperature. You see, this is a solubility curve, and I'm highlighting some key concepts in orange. This curve here is the saturation curve, meaning the limit of salt that you can dissolve in 100 grams of water, and anything above this line is a supersaturated zone, meaning that there are more salt dissolved than should be possible. If you go up this curve, meaning you start from bottom here and start evaporating water, you start to increasing your concentration. So eventually you will hit this line. Similarly, you can start from somewhere and cool down your solution to the left. Eventually you will also hit the saturation line. This is how most seed crystals are made. We dissolve a high amount of salt in hot water, and when it cools, it forms some crystals that are later used for crystal growth. That's why they are called seed crystals. But this process of forming crystals is called nucleation. It's not uniform, meaning the concentration gradient is not locally uniform. You might have fluctuations of concentration around the solution. Maybe the center is hotter than the borders, and then you have regions around that crossed that limit, but the center didn't, and as well as near the surface. And then you form a lot of seeds. It also matters the geometry of your vessel. Maybe your geometry has some spot that favors nucleation, right? Favors the concentration and then the formation of tiny crystals. That's why when temperature changes drastically, you get some strange effects, like when you have a nice crystal and the temperature goes up, your concentration goes down, and then your crystal dissolves. Likewise, if the temperature goes way down, your concentration goes up very fast and your crystal grows very fast, which will change its geometry and maybe its transparency also. We'll talk about that later. Right, to understand future informations, we need to think about evaporation on a molecular level. So let's give this water here. We have water molecules in liquid state and water molecules in vapor state. All molecules have some kind of energy, kinetic energy. They are bouncing around all the time. That's the definition of temperature, the average kinetic energy of the molecules. So eventually some molecules will jump off the liquid phase and transition to the vapor phase because they gain enough energy, and some molecules from the vapor state will lose enough energy and come back to the liquid phase. When this happens at the same rate, molecules going up, molecules coming down, it's an equilibrium, and we see that as nothing's changing. The volume of the liquid keeps the same. But if we heat this liquid up, we are essentially giving the molecules more kinetic energy, so more molecules will be able to transition to the vapor phase. In the result, we see the liquid phase reducing, and we see it evaporating, right? There's a net outflow of molecules from the liquid to the vapor phase. Temperature also affects crystal morphology. After all, the crystal compounds are also vibrating. Here you can see in this information how magnesium sulfate crystals change their shape according to the temperature of growth. So the temperature can also affect your crystal shape. Also, not only the temperature, but the temperature change rate might shape your crystal in a different way, as you can see in this graph from this study down here. I have some photos of some sodium chloride crystals that I grew a time ago, and you can see how that shape is right here. Okay, so we talked about how temperature can change your concentration, but of course, if you add water to your solution with your crystal inside, you also go down the solubility curve, and then your crystal would start to dissolve and vanish slowly. Then, my dear viewer, you might ask me, oh, wait, why would I add water to my solution? And that's the thing, maybe you wouldn't, but nature would in some conditions. We already seen that if temperature of the solution goes down enough, you have more molecules coming down to the liquid phase than molecules going up to the vapor phase. So you're adding more liquid to the solution. Also, there's an important concept here that I want to share with you. There is vapor pressure. Right, so from this scheme we have the water in the liquid and vapor phase, and as the vapor phase is a gas, it exerts gas pressure on the vessel walls and on the liquid surface. Under the right thermodynamic conditions of equilibrium, meaning that state where there is no net outflow or inflow, exchange of molecules between those states, we have a constant vapor pressure depending on a few things. In this case, this kind of liquid, which in this case is water, and the temperature. This is called the saturation vapor pressure. If the actual vapor pressure is higher than the equilibrium state, the saturation vapor pressure, you have condensation, because there are more energy in the vapor molecules than the system can handle at the moment, so they will turn to the liquid state. Conversely, if your actual vapor pressure is lower than the saturation, like in this extreme example of a vacuum, the molecules will rush to fill this energy gap through evaporation. So they will do it until the equilibrium is restored. And again, we come back to here. For water, we can find some tables of known values of temperature and their saturation vapor pressure. The ratio between the actual vapor pressure and the saturation is called the relative humidity, a very known concept related to comfort. You might have heard about it when you think about drier air conditions, like some place with an air conditioner and the humidity is too low, so your eyes are burning or just uncomfortable. Or likewise, when you are on the opposite side in an ambient with a humidifier and the relative humidity is high, and you start sweating a lot and it seems like the sweat doesn't evaporate and you're still hot. That's because it doesn't evaporate as efficiently. If you want to know more about it, check out this data on humidity. This is an index relating comfort to the temperature and the relative humidity of an environment, and also check out these key concepts to know more about how relative humidity plays a role in your life. Okay, so how relative humidity affects our crystals? Well, from the equilibrium, we have seen that the water molecules attract the salt atoms, salt compound atoms, or the ions. I'll just call them atoms from now on. Likewise, if the water molecules are attracted to the solute is also attracted to the water, and so this force reduces the amount of water molecules that flows from the liquid to the vapor state, because more energy is needed, not only for the molecule to change its state, but also to break this bond, so it has enough energy to transition, meaning that the vapor pressure of solution is different from the vapor pressure of pure water. And if we check this out, this ratio between the saturation vapor pressure and the actual vapor pressure is the relative humidity, meaning that if I have a solution instead of pure water, my vapor pressure will be lower, so will my relative humidity. For some solutions, a bunch of studies, very well consolidated studies, shows that there are some fixed points. Is the equivalent for the saturation, the equilibrium saturation vapor pressure, but not to water, but to the solution. So in this case we have sodium chloride here, and we can see that from this range of temperature, the usual temperature range, at least for the place where I live, it's around 75%. What does this mean for your crystals? Well, let's check out these scenarios. Right? First, if your relative humidity is lower than the equilibrium and you have some solute over here in your saturation solution, what happens that water evaporates because it will tend to bring the relative humidity back to the equilibrium, so it will lose water, and in turn your salt will precipitate. If the relative humidity is the same as the equilibrium, we don't have a net exchange of water between the vapor and liquid phases, so it seems that nothing is happening. On the other hand, if the relative humidity is higher than the equilibrium, we will have more water coming in your solution, and it will dissolve your salt. But if your salt amount is too little to handle this absorption until the equilibrium, there won't be enough water absorbed from the environment, and your relative humidity will still higher than the equilibrium. What does this mean for your crystal applications? Well, let's assume you have a nice crystal on the solution, and you are checking out the environment conditions with a simple thermal hygrometer, right? It tells you the humidity and the temperature, which now you know it's important. So let's say this is a sodium chloride crystal, and we know that its equilibrium humidity is 75% at 25 degrees Celsius. So when the relative humidity is lower than 75%, my solution is losing water to the environment, and so my crystal is growing. If my relative humidity stays the same, then nothing exciting is happening. And here comes the danger. If my relative humidity gets higher than 75%, my solution will absorb water from the environment, and then the process of crystal dissolution will begin. If it stays on this state for too long, my crystal eventually will vanish. This also affects crystal quality. You see, when the evaporation happens, that water molecule that was binded to a crystal atom is gone. So this atom is now lonely, and it is on an unfavorable energy state, and we try to equilibrate that so it can nucleate a new crystal on the surface or somewhere nearby on your vessel, or it might join another crystal because it's energetically favorable to just join another crystal lattice around, or it will take another spot and the water molecule associated will leave that atom and join this one, and then this one will do the same, and so on, so on, so on, until the last atom over here join a crystal or nucleate. Of course, this happens in a lot of atoms and a lot of molecules at the same time. This thinking process of a single molecule and a single atoms just for illustrate. So variables that control this: temperature, of course. Temperature not only because of the things I've already showed you, but also because temperature changes chemical reaction speed. Also the distance. Imagine that your molecule, your atom, is too far from the crystal. You probably won't have enough energy to just make all the way through to get that crystal. You probably nucleate on the surface or find another crystal, or just hang on to some impurity. That's why purity is right here, like a dust grain, or I don't know, something that's an impurity on your solution. It might even be another compound. Not every water is chemical grade pure water, so you might have some other compounds that make it nucleate around. Remember, this is always a question of energy, so where the conditions are thermodynamically more probable to induce crystallization is where it will occur. Also, time is a very important variable, as we will see on the next slides. Right, so how time influences this thing? Imagine that your atoms have to form the crystal, so they have to get together and they have to arrange themselves around the existing crystal, so they have to just find their way to the right spot along the lattice to keep your lattice uniform. Doing that, your crystal grows uniformly. But consider the following hypothesis. If your crystal, let's say this is the crystal, and there's a bunch of atoms, there's too many atoms coming down to join this crystal, they probably won't have enough time to find their way to the best position along the lattice. That's why sometimes with higher evaporation rates we get these kind of strange and fractal-like crystals from the sodium chloride, which should be cubic. Also, this might form crystal with defects, even if the growth is uniform, meaning the crystal grows like a cube. It could get defects because there is not enough time for your atoms to arrange themselves properly. Check out this very cool material on the Crystal Growing Wiki about crystal defects. So from these pictures, from the crystalverse, you can see that under three different conditions, the sodium chloride showed different quality, right? For low evaporation, we have this very nice edgy prism-shaped transparent crystals. Then with a slightly higher evaporation, we have these so-called ghost crystals, which are these white inclusions on your crystal. Also check how the cubic shape is lost within the same crystal, right? We have some growth, some side growths, and for higher evaporation we get the crystal with even more defects on the crystalline arrangement, meaning that that should be an alignment in this direction, but this one grew in this direction, and then this one got another direction, and so forth, and they are very opaque. You see, the faster the evaporation, the white the crystal get. This is probably because the lattice is not aligned, so light scatters on the lattice. But we are talking about evaporation and low, medium, and high evaporation. You might ask me, how much is low evaporation or high evaporation. I also asked that myself and got some interesting results. To talk about evaporation rate, I want to cover the solution surface area and the crystal size. So, for solution surface area, imagine that we have these four scenarios. Okay, we have surface area higher in this scenario over here, with just water over a sheet, and the smaller surface area would be this one on a thin tube. So, as evaporation is quantified by water mass evaporating over time, we might conclude that the more water we evaporate, the bigger the surface area. Logically, for a same-sized crystal, the faster my evaporation is, the closer I get to that condition where the atoms won't have enough time to arrange themselves properly, while in a condition with a smaller surface area, I'll have a lower evaporation rate, and so the atoms will have more time to arrange themselves properly. Of course, this has some specifications. The concentration of the solution is important, and also these conditions over here where we are talking about a sheet and water over it, like droplets, they have their own phenomena happening that change the way evaporation occurs. You can check more on that in this paper. But in general, if you consider the other three scenarios where we have a flat surface, we might assume that the amount of water that evaporates from a patch over here, the S1 patch, should be the same amount of water that evaporates from the S2 patch if they have the same surface area. In this case, we are talking about the water mass that evaporates over time by the surface area. Okay, let's keep that in mind and talk about the crystal size, or should I say crystal surface area. Have you noticed how after a certain length the crystals get transparent in the same conditions? I mean, this picture, I didn't change the environment conditions, so the evaporation rate over here, the relative humidity was the same, the temperature was the same, so the evaporation rate changed very little due to the surface and some phenomena, but the major conditions were kept the same. And after the crystal got some size, it became transparent. Let's imagine that's in the beginning, when the crystal was smaller than this, we had this scenario of fast evaporation. So the crystal was small, there was a bunch of atoms coming up, and they didn't have time to align themselves to the lattice. But later, when my crystal got bigger enough, the same amount of atoms now would have enough surface to distribute themselves and align properly with the lattice, keeping it transparent like it should be. So from this condition, it's not so fast. You can think of this like parking in an organized environment where everyone parks their cars on the right spot against some place where someone did the favor of parking in the wrong place. Since this guy over here is on the wrong place, the following layer will not be on the right place until a few moments later, where the arrangement will restore the uniformity. This is pretty much what's happening here. You have a misalignment of the crystal lattice until we got the right conditions so that the atoms can arrange themselves and restore the original nature of the crystal. I have some more images about this evaporation rate over here, so you can see from this test that we have first some white crystal forming, right? They formed by evaporation to the environment, and then some new crystals formed, but these new crystals formed transparent under the same conditions, just because there were a bunch of opaque crystals before. Now the new crystals are transparent, and not only that, but the old crystals are also getting a transparent layer due to this new evaporation. So this brings to the discussion of the so-called parasite crystals. For long in the community, I've seen people talking about how another crystals on the solutions are bad to your crystal growth because they suck up the coming atoms that should go to your crystal, so your crystal growth is slower. But actually, these parasite crystals, they're actually getting the excess of the solution, so they are helping your crystal to grow in a controlled manner. So I prefer to call them buffer crystals. They are friendly. And again, you might remind me that we got on this part of the video think about how much is a fast or slower evaporation. So I made this scheme, this apparatus, to weight the crystal evaporation. So I have an airtight container with a servo and a solution vessel over here. This is a scale that I made with a simple scale, and in this environment we have a fan to uniform the air, some temperature and humidity sensors, and a dissecant, which in this case is silica gel. These things controlled by the Arduino, and I think on sharing it in the future. But for now, this is the apparatus. Right, this thing went inside a controlled temperature environment, which is the crystal chamber I'll talk about later in the video. And this is the data, this chart shows the data that I got of multiple conditions, multiple tries, and these ones are the transparent crystals and these ones the opaque crystals. And the surface area of the crystal, as you can see, there seems to be a boundary over here from which, if the surface area is bigger, then for a constant evaporation rate you have the crystal growing transparent all the way through. But if your evaporation rate gets higher than this threshold, then you get opaque crystals. That should be the fast evaporation. Or if you have some evaporation rate over here, you should have a surface area enough to cover for this to grow in the transparent domain. Otherwise you get opaque crystals. Of course, is unknown for now with this data that I got, which is from August 2024, if this domain have a continuation this direction or this direction. I'm just not sure yet. There are more data needed to fill up this gap, but from now we get a very nice look on how the crystal growth changes under the evaporation rates at least for sodium chloride. Then you might ask me, okay, this is a home science video, isn't it? So how can I measure evaporation rate at home without all these things? Okay, I have some good news, which is the correlation between the evaporation rate and the relative humidity of the chamber, at least for sodium chloride. As you can see, it's pretty linear, meaning that the rate is directly proportional to the chamber relative humidity. So you see here that for 75% it's almost zero, and this is in agreement with that article about the sodium chloride equilibrium humidity. Also, there's the influence of the surface area of the solution, so you can check on your arrangement the surface area of your crystal, right? You get it? Let's say you have something around here and you check under the domain for transparent crystals which evaporation rate is the maximum amount that you can provide. From that information we go on to discharge and check the minimum relative humidity that can be achieved. Anything below this will provide a higher evaporation rate, and you probably end up in the opaque part of the chart. So use these hygrometers to check your conditions and know your minimum for your crystal surface area, and then you can verify if your crystal are growing in a healthy way. Of course, this is for sodium chloride, so for other types of compounds these equilibrium values might change. Even this correlation between evaporation rate and relative humidity might change. So maybe this video will also incentivize the community to produce this kind of data and help us produce crystals of other kinds. What about the solution surface? You might think about the vessel that you use to crystal evaporation. Well, this is a closed system. It's important to remember that. So let's say this is your limit from the previous step, and you have a closed system with a vessel. So you multiply your surface area with this evaporation rate, and you get the evaporation rate of water per hour. Remember also the relative humidity concept involves the amount of water in the air, so that's represented by the vapor pressure. So let's say you have a dissecant here, so you can keep in steady evaporation, let's say from an amount y, and your solution evaporates an amount x. If we check what's happening in a very illustrative way, your solution will begin from the equilibrium and will lose water to the dissecant, so the relative humidity will fall for a while. As the humidity falls, your solution enters a region where it starts to evaporate, so it will recover the relative humidity to an equilibrium, let's say 74%. Then you check if 74% is above your limit, and if it is, nice, you can keep it like that. Your crystal should grow transparently. But let's say you have 3 times more dissecant, meaning that now you're drying the air three times faster. So in this case, your condition from the equilibrium will fall very rapidly, and your solution will rebound and find a new equilibrium, let's say around 72%. That's just too dry. The solution will evaporate too fast, and your crystal probably will lose quality. But if you have the same crystal, the same amount of dissecant, but now a surface area 4 times bigger, you will have 4 times more water coming out for the same evaporation rate. If you check how things should happen, then you will start from the equilibrium and will start to fall down the relative humidity, but your solution will start to evaporate. As your surface area is bigger, then more water will go to the environment, and then this will bring to an equilibrium in a value much higher than the previous step. So it might even be better than the first condition, and you also have a nice evaporation condition above the limit. Just some data over here if you want to check how wider surface influences the amount of water that is being evaporated to the air. Right, so how buffer crystals get in these equations? Let's say this is my domain. This is just an extrapolation from the linear conditions of boundary over here. So let's say you have a crystal and it's just sitting over here. If you have buffer crystals, you have more surface for this material to attach, so your effective surface area grows, meaning that your crystals might handle now a bigger evaporation rate within the transparent domain. This translates to a drier condition. This is an example of what I just mentioned. This is just a tray, a plastic tray, and I had a bunch of tiny CD crystals, and you can see they kept their shape, their quality, and transparency under some conditions that should be that condition of opaque growth. Also, you can use this information to produce some very nice custom-made crystals. You might start with an opaque crystal, and then it grows a transparent border, and then you might want to put another white coat on it. It's versatile. Okay, about vessel geometry. This is another question that we usually see on the community about the kind of vessel that you use, the amount of solution, or the shape. So if you have a nice cylindrical or square, whatever thing your vessel looks like but it's even, then you should have an even distribution of concentration around the solution. But if your vessel is too big or has a strange or curved shape, you might have a momentarily uneven concentration on your solution. You see, this is a big surface area, so you will have a lot of evaporation happening here. You also have these curved shape that might separate your concentration somehow due to temperature fluctuations or whatever. So that might change how your crystal grows. Also, be aware that as your solution evaporates, it will eventually be on another height, so the surface area will be smaller than on the beginning. And as we have seen, surface area change your evaporation rate, which changes your crystal quality. Another consideration is the distance. If your crystal is too far from the surface, it won't have enough time, nor it will be energetically favorable for your newly free atoms to come all the way through your crystal. They might just nucleate near the surface. Likewise, if your crystal is too close to the surface, they might have access to the atoms too fast, and then you might have uneven growth. Or if the conditions change, let's say your relative humidity falls below the equilibrium, since your crystal is too close, the newly coming water molecules will just dissolve your crystal locally, and that's also not cool for your quality. The preferred arrangement, of course, is the even distribution. You might achieve an even better distribution with steering, like with magnet steering. I'm still testing this out, so I don't have much information on it. Also, be aware that the shape of your vessel might change your relative humidity on the vicinity. Meaning, let's say this arrangement is on a low relative humidity environment. Since the water molecules can't make a good exchange over here, you have a high relative humidity near the surface, even if you are in a low relative humidity environment, if the vessel has a smaller opening. You can see in this video the example of changes in concentration. These are citric acid crystals, and you can see on the shadow these wavy-like shadows along the crystals. These are light refraction phenomena, because the density of the solution changes with the concentration of solute. So in the vicinity of the crystals, the density is just a little lower than the rest of the solution, because those atoms that were dissolved are now on the crystal. So this area over here is a little less dense, but just enough for light to refract in a different way and to produce these wavy-like shadows. Okay, so let's cover wind and vibration. Given that you have an environment with a low relative humidity, low in this scenario meaning that your relative humidity is below the equilibrium, your solution will have a high relative humidity near the surface due to evaporation. So this gradient of concentration of water vapor will produce a transport of mass, mainly driven by diffusion, which is quite a slow process. If we add wind to this scenario, then more evaporation will happen, and we can easily see why. From that diagram with the water molecules, we can see that if wind is applied, then we are carrying away those water molecules from just above the surface of the solution. So more water molecules will be coming out of the solution than coming in, and this net flow of water molecules translates to more evaporation. Of course, this is where the vessel geometry comes in place, because in the second case, the molecules just above the surface are protected from direct wind, and a few of them will come out from this smaller opening. So your relative humidity here will be higher than on the open vessel, and this will also change your evaporation rate as we talked before. About vibration, there isn't much information on how vibration might change your crystal as far as I know, but for sure it affects nucleation. You know, those random fluctuations of concentration and disturbance might produce some nucleation around your solution. As you can see here in this supersaturated citric acid solution, there was a disturbance, and then crystals start forming around the nucleation site, and then the solution went on crystallizing because it was supersaturated. But you can see from this example how vibration and disturbances can start and affect nucleation. For more complexity, you can think about using multiple compounds, controlling or adding impurities and additives. I got some examples from the Reddit community to show here about additives and multiple compounds. In this first image, you can see that a little bit of EDTA was added to the sodium chloride solution to trap some metallic impurities, and that produces a crystal that's very transparent and clear. From the second example, you can see the usual shape of alum, which is this diamond-like shape, but if borax is added to the solution, then alum tends to crystallize in a cubic shape, which is quite interesting. There's also some examples on the community about coloring, so it's worth checking it out. For table salt, which is our primary source of sodium chloride, you have to remember that some food additives are added to it, and they might change your crystal shape and the results that you get as well. Also remember, when dealing with different compounds, that each compound has its own solubility curve, and there might have some strange shapes and strange behavior over temperature, making it more susceptible to temperature changes or not. So it's always important to check it out before trying your crystal growth. Then for the end, you might ask, what about pressure? Well, pressure is not the kind of thing that I heard too much associated to crystal growth. Maybe because it's not that easy to handle pressure in home, but maybe pressure might change your crystal in some way. It's something that I didn't study in depth, so it's an open topic for now. Well, you finally grow your crystal, you should be able to hang it and let it shine forever, right? Not quite. Remember about the influence of the relative humidity and the hygroscopy of your crystals. They were water soluble after all, meaning that the water molecules on the air will also be trapped in your crystal surface and dissolve your crystal in the air if the relative humidity is above the equilibrium humidity. This is the same principle why some dehumidifiers like calcium chloride, it's how they works, right? So check this curve for vapor pressure of calcium chloride. Ambient temperature of 25 degrees Celsius, we can see that is the vapor pressure, and we divide by saturation vapor pressure, and we got the equilibrium humidity for that concentration, which is around 30%, meaning that if your environmental humidity is higher than that, then the material will absorb water from the air and your crystal will vanish. Search for the liquescence for more information on that. So we need to protect our crystals. One way is to cover it with something transparent, just to form a barrier to the water molecules, so they won't find your crystal surface. You could use some glass kind of box or something to store it in it. Some people have suggested nail polish, but the problem with nail polish is that it gets yellowish over time, so you lose your crystal appearance. And here is my tip. I have found some nice results with acrylic varnish. This example over here is one of my sodium chloride crystals, which I applied some cover with acrylic varnish, and it has been like a month now, and the crystal is very well. I haven't have any trouble with it, not whatsoever. Okay, so enough theory. Now we get some practical part of the video. So I'll cover these three topics. First, an easy project. This is a crystalloylite. It is an hydrated form of sodium chloride, and to produce this thing you need to check the thermodynamic conditions on what is called a phase diagram. If this is new to you, a phase diagram is just a chart showing which phases are stable under certain thermodynamic conditions. In this case, just temperature is needed. So here we have the concentration of sodium chloride in water, and here the temperature. You can see that from this area over here, things will be on the liquid phase. So if you just start with a liquid solution with sodium chloride on it above this concentration, let's say like here, and just cool it down below the freezing point, you get a liquid solution and the crystalloylite, which is this thing. Crystalloylites crystallize in these very interesting hexagonal-like shape in layers, so you have multiple sheets of the crystal, and it forms some really cool patterns to look at. The problem is they are unstable on typical temperature, so if you take them out of the fridge and stay looking at them for too much, they will melt down and the salt will be released, forming these kind of process. So you have to keep them in the fridge or at least below 0 degrees Celsius to conserve the crystal. But it's a very simple project to do. It might be your start on crystal growing, and some very cool patterns can arise from this. For evaporation control, a simple way to control evaporation is the use of what I call a binary system. You see, if you have a closed environment with two solutions that have different equilibrium relative humidities, you might get a net transport of water from one solution to the other. So in this case, I've been using sodium chloride in a little crystal, which has an equilibrium humidity of 75%, and in the other vessel I have just put a bunch of citric acid and solved it to the limit, and just added more citric acid, so I have enough material to keep water coming in, which in this case citric acid has an equilibrium relative humidity around 74%. The results that the water transfer was almost constant in this system, and the rate was like something like 0.9 milligrams per hour of water from the sodium chloride solution to the citric acid solution. In this case, I haven't used any kind of wind or temperature control or anything else. Right, for more advanced control, I developed this machine that I call crystal chamber. So considering all the variables that we talked about, I made this schematic here where we have the solution under a closed environment. There's the dissecant, in this case silica gel. There's a trapdoor to regulate how much air comes in to the dissecant chamber and gets dried out. So if I need more dryness, I would open the trapdoor. If I need a slower evaporation, I would close the trapdoor. There are some temperature sensors, a fan for air uniformity, and this is airtight. It's that arrangement from before, but without the servo and the scale. In this case, just the solution, the vessel, and everything else. For temperature control, I made an insulation chamber here. So this is just a styrofoam box which serves as a temperature barrier, but we need to keep the inside cool. So I've used a Peltier element with some heat sinks and fans to cool down the insides of the chamber, pumping out the heat. All this is controlled by an Arduino unit, and that's why the sensors are positioned in various strategic positions. So this airtight box goes inside the chamber, right? And here's the unit. Here is the box, the heat pump, pumping out heat from the box. And this is a little monitor that I'm making to check the progress and how things are working. And there is also a sensor over here to check environmental conditions to regulate the power of the Peltier element. Here are the results in charts. So you can see on this orange line over here the external temperature, and here the internal temperature. You can see that those two are correlated, and that's because the Arduino is regulating the power of the thermostat, which is in this case the voltage for the Peltier element. So I'm improving this algorithm, but it's really nice for now, as the temperature inside the chamber was really close to 25 degrees. For the relative humidity, the orange line is also the external variable. So here we can see a lot of fluctuation on the relative humidity, and also it's very below the equilibrium point, so it's not good for crystal quality. In gray is the line of the silica gel. As the silica gel saturates, this curve will go up, and when it hits like 73% or something, I won't be able to remove water from my solution, so I have to reset the silica, put new silica to the chamber. We can also see that the solution started near the equilibrium point, and then it slowly went down to near 73%, where it stayed over the course of like 50 hours in this series. Here are the ranges of the series, and as you can see, the internal temperature stayed very steady, with a variation of 0.4 degrees Celsius. The internal relative humidity also stayed steady, varying less than 1%, and this can the relevance of this can be seen by checking the external relative humidity. There, not only the value is too low for a good crystal growth, but it's also varying a lot. This has a significant impact on my evaporation and crystal quality. Some more information. The thermostat power is still a lot of room, so if environmental temperature goes really up, I still have room for more cooling here. And in this series I got a mean evaporation rate of around 2 milligrams per hour, producing this tiny sodium chloride crystal. This is the evolution of this crystal over the course of 17 days. So as you can see, it started on a thin thread as a very nice and transparent crystal, and it kept growing in a cubic shape and so forth. So here in the pictures below you can see it evolving through the days. You might also notice that my crystal got some scratches on the surface, and that's because every 2 to 3 days I was opening the chamber to take some pictures, and eventually I let it fall. I know that's a shame, but it's part of the process. So hopefully the crystal will recover from these scratches. They have some really nice approaches to crystal growing too. They use different methods for crystal growing. I use evaporation, they use concentration gradients and other stuff, but it's very worth watch them. Also check out Crystalverse. This amazing website has some really cool information about crystal growing, and especially about sodium chloride, the conditions and some tips on doing it yourself in a simple way. Also check this amazing book by Holden and Singer talking about crystals and crystal growing. They will cover all of these topics much in depth than I did here, and it's very interesting. Also check some other channels. I have some of my favorites here, and also the crystal community of crystal growing on Reddit. Go there, share your crystals, share your ideas, and let's make this fun for everyone. So this is the end of the video. If you learned something new, then this purpose of home explanation was fulfilled, and I wish you good luck in your crystal growing attempts. So I consider myself to be a scientist by nature, meaning that I make a lot of questions on how things work, and I really like to learn how nature works and what can we do with that. I ended up getting an engineer degree, and while I was studying material science, I came up with this subject on crystalline arrangement of atoms, and these pictures and models of sodium chloride crystals. They are really pretty but very tiny. So I shared this up with my dad, and he asked me one day, can we get a bigger crystal of this? Like just make it bigger and keep it transparent and beautiful. And then I thought initially that if we took water out of the solution, the atoms should arrange themselves and give us a nice crystal, right? Not quite. If you ever let salt water evaporate, you probably ended up with something like this, a white crust of salt. So I went to the internet and started searching, and found some channels like this one that showed me that was possible. So I've been on crystal growing since then.